Hello everyone, welcome back to the channel. Welcome to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant with technology and prepare for the future. Today I thought we would discuss a little bit about how to send some signals to an ADC. For those of you who don't know, an ADC is the acronym of analogic to digital converter. It's a device that basically links the analogic world, the world of voltages, currents, and so on, with the digital world, the world of microcontrollers or computers, the world that works with ones and zeros, with basically information and uh, not just voltages. So apparently these things at first glance these things are easy. You have an ADC with one or more inputs, and well, you apply voltages to those inputs. However, in reality, we're not supposed to directly apply voltages, at least not bipolar voltages, to those inputs. We're supposed to, well, convert those voltages into something that the ADC accepts. And this is something that I made a mistake back some months ago when I built myself a device, and I did not knew enough about ADCs. So now I made a bit of research on the internet, and I found out how I was supposed to do those things. So I thought, why not make a video to show you as well, and so you can make things the right way from the beginning instead of making mistakes like me. So let's discuss a bit about the ADC itself as a general concept. Okay, we're going to ignore this for a moment. This is the circuit that I will be showing to you, and I will also be showing actual results from testing this circuit. But for the moment, let's just go into a different data sheet, into a different schematic, and let's explain what we want. So if we have an ADC that has multiple inputs, and we want, there are two kinds of voltages that we could potentially convert into information with an ADC. There are positive voltages or so-called unipolar signals, and there are also bipolar signals, which is the case when we have both positive and negative voltages. Now, if we have unipolar signals, and by the way, to make things a bit more clear, unipolar signals is when all voltages or all the values have a single sign, typically plus. In other words, all the values that we are having in our signal are most of the time positive or just negative with respect to a certain ground. So their sign does not change, only their values changed. Okay, this is equivalent to DC, direct current, right? It can vary its voltage, but it can never vary its polarity. This is unipolar signal. On the other hand, a bipolar signal is basically AC, alternative current. It's a signal that changes not only its value, but also its polarity in time. It goes negative as well as positive. Okay, so if we have only positive voltages, those can be just directly referenced to the ground of the ADC, most of the time, and those can be applied to the inputs of the ADC. Okay, of course, the ADC accepts a certain voltage as its maximum on its input, so we will have to take care of that. If our voltages are higher than those maximums, then we need to use, I don't know, voltage dividers or stuff like that. But essentially, it's as simple as just applying that voltage to that input. Now, if we have voltages that go below ground, okay, like I said earlier, if we have bipolar signals, voltages that are both positive and negative, some ADCs allow us to use pairs of inputs in order to evaluate those voltages and have both positive and negative values. However, it is very, very tempting to think that we can and that we should simply apply those voltages to those two inputs that make a pair, okay, like in this circuit, and that everything's fine. Well, not quite. Yes, if we have a single voltage, we can do this. That voltage can be both positive and negative, so the plus polarity can be at either of these two inputs. However, it's not the proper way to connect such a voltage to an ADC. And although this works for one voltage, when we have multiple voltages, it will not work anymore and it will cause problems for us, okay? And this is something that I've done in a previous project of mine. I did just that. So in a previous project of mine, I had the ADC, which obviously needs to be powered by some digital voltage, typically 5 volts. It has a ground of its own. I symbolized here with the ground digital, ground D here. Now, internally, each input of the ADC is connected to its ground. Not in a direct way, but there is an impedance that exists between each input and ground. So I have symbolized that impedance through these 4 resistors, one for each input, which are external in my schematic here, but these are just for us to properly understand what's going on, okay? These are not actual resistors on the outside of the circuit. I'm pretty sure they are not actual resistors on the inside either, but these impedances do exist, okay? And they are here just for clarity's sake. And so with my analogic signal, I thought, hey, okay, well, I'm going to have 2 signals. Both of them are bipolar. So I'm going to use, of course, all 4 inputs. And I'm going to say, okay, let's have input 1 and input 3 as an analogic ground. I will connect those 2 together and tie them to the analogic ground. And relative to those, I will put input 0 and input 2, those 2 voltages that I want my ADC to measure, okay? And I thought this is perfectly fine. Well, it is not. And back then I could not visualize this thing with resistors. Now I can. So we can clearly see that if we do this, we will have a voltage divider between all analogic inputs and digital ground, and of course the analogic output, sorry, and the ground. But these voltages, these analogic outputs, also connect to the analogic inputs. So when we have such voltage dividers, we will also risk applying negative voltages on the inputs of the ADC, and that's a big no-no. Okay, we're not supposed to do that. The ADCs don't like negative inputs whatsoever, and they actually have some internal diodes, Schottky diodes, to clamp these voltages and protect themselves against negative voltages and so on. But anyway, overall, it will most likely not break the ADC, but it will definitely make the ADC not evaluate those voltages correctly. Okay, and that's a problem. So this is a big no-no. Instead of doing this, we need to take those signals, those analogic signals, and convert them to a pair of voltages that both need to be positive, but one in relation to the other can be smaller or higher, and therefore the difference between them can be positive or negative. And this is the way we're supposed to do things in order for the ADC to not have a problem, and also to evaluate correctly the voltages there. Okay, so this is what we are doing with this schematic. Now, a version of the schematic can be found on the internet. However, that particular version I found to be not so well working. Okay, so what I found on the internet is this configuration with two op amps, both in non-inverting configuration, and they were also providing some amplification factor. They had a resistor between their minus input and their output, and that's it. That was the entire circuit. Well, I found that one to be problematic. Okay, so I found that I need to add some components on the input. Okay, also, so we are having this signal here, this bipolar signal, which is symbolized by this circle with the signal with a sine wave on it, and our goal is for its values, its voltage values, to be measured by the ADC on the far right side of the screen. Okay, and this is an ADC with two inputs. We're going to use both of them in order to evaluate this voltage, which can be both positive and negative depending on, well, the moment that we are evaluating its voltage. So the circuit that I am presenting you is the one in the middle. Okay, this is why I created connectors to clearly state that the circuit is just the one in the middle. It's not the one on the left or on the right. So what we need to do is take this voltage that can be both positive and negative, and from it create two voltages on the output that are absolutely positive no matter what. Okay, and those voltages can be safely sent to an ADC. Okay, now this circuit of course must be powered, and I chose to power it from a 12 volts, a single power supply. I chose to play with the absolute cheapest and simplest op amps that I could find on the market, or one of the cheapest ones at least. AS358, which are the cheaper equivalent of LM358. Okay, if we buy 100 of these, at least from this distributor, they are about 10 cents a piece or something like that. So they are a double op amp integrated circuits. Okay, so we have two in a package, which is great because we need two for this circuit to work. For me, they are in a buffer configuration, meaning I've just tied the minus input to their outputs. I don't want any amplification or attenuation. I want the input signal to be precisely given on the output, okay, without any form of amplification. In my case, of course, in a different case it could be different. But on the on the input and also around the op amps, I felt the need to put some more components. Okay, so I saw the need of putting these relatively high resistors, 560 kilo ohms, in my case, but it's not a critical value. You can put it smaller ones or bigger ones. I felt the need to put these resistors between the minus of each op amp and the plus input of the other op amp, because they provide a little bit of extra stability. Without any component, the circuit is unstable and also has the risk of receiving short negative voltages on its input, which causes the so-called phase reversal on the output of the op amps. Okay. In other words, the signal might look like this, which is not desirable. With yellow and blue, we have the two outputs. Okay, the outputs which are U1 and U2 here, and with magenta, well, it looks more like red here, but it's magenta actually. We have the mathematical channel of the oscilloscope, which calculates the difference between the yellow and the blue. Okay, in order for me to see what would the output voltage be like if I would reconstruct it from the two positive voltages. Okay, we have the zero line on the inputs here and the zero line on the mathematical channel here. And as we can see, we have these very high peaks which go above, they get out of the screen. We have 1 volt per division for all channels. So we have 1, 2, 3, 4, 5 for the mathematical channel. At the maximum, these peaks go above 5 volts for very short amounts of time. This means that in these particular moments, and we can clearly see the signal on the yellow channel, which is basically the signal that one of the op amps puts on the output, but therefore also the signal that one of the inputs, one of the op amps sees on the input, goes below the absolute minimum value. It goes negative, you know, and because the input signal goes negative, the output of that particular op amp goes to the maximum voltage possible, and overall we get this annoying and not desired behavior. Okay, we must prevent at all costs the op amp from receiving negative voltages. So in order to do that, I have decided to put Schottky diodes on the input. Okay, I have decided to use a voltage divider with the 1 megohm resistors. It can be higher, it can also be lower, but careful about what we're putting here, because this will present itself as the input impedance for whatever circuit we are connecting to its input. Okay, so it cannot be too small, otherwise it will start drawing current from too big current from the input device in the input circuit, and that circuit might have a problem, and we might overall have a wrong reading. Okay, I have put these clamping Schottky diodes with the cathode to each input and the anode tied together to this middle point. Okay, this middle point, this middle point of the voltage divider gets connected to the negative wire of the supply voltage for these op amps. Okay, and this will also be the ground for the output voltages. And I have also decided to put some capacitors here, in my case 100 nanofarads, but their values will have to be calculated or determined experimentally based on the maximum frequency that you want to have in this circuit. 100 nanofarads can potentially be just a bit too high. In my case it was okay. I put them here in order to also provide better stabilization of the whole circuit, especially because since this whole circuit has a high impedance, it is very susceptible to picking up 50 Hertz, or if you're in America, 60 Hertz noise from the power cables in your walls, and basically amplify them and send them on the output. And needless to say, we don't want that. So I've put these capacitors in order to basically reduce to the absolute minimum that annoying hum, that annoying electrical noise that gets induced, especially if we are working on a breadboard. Okay, that noise gets easily induced in the wires that we use on the breadboards, and they are overall annoying, not desired, and a problem that we want to eliminate. And essentially this is the entire circuit. Okay, it's not a big rocket science. Whenever we have plus on the upper wire and minus on the lower wire, the first op amp, the one on top, works because it has positive voltage on its plus input, and it will give it on the output on U1 output voltage. Also the lower op amp will be basically, it will not work, it will not do anything, so it will output 0 or close to 0 volts on the output. And when the polarity flips, well, simply the whole thing flips, because if we take a look and if you draw a horizontal line about halfway across the circuit, you will see that so kind of like this. Okay, you will see that the circuit is symmetrical. Okay, we have the exact same thing on the upper part of the circuit as on the lower part. So when one op amp works, the other is sort of disabled. It will give 0 volts on its output, and this is how the whole circuit works. Okay, and it actually works. You want to choose the lowest, the Schottky diodes with the lowest dropout voltage. I used these ones because these were the only ones that I had. These are okay, because the AS358 specifies that it actually does accept minus 0.3 volts on the input. It's not much, but it's okay, you know. So it's not a big problem. And by the way, the 358 is just a dual op amp version of the 324, which is the 4 op amp version of the of this IC, of this integrated circuit. Okay. So yeah, so that's pretty much it. Okay. It's not a big deal. It's not rocket science. Now let me show you some results in order for before I show you some results, perhaps I should explain again what we are doing here, but in a visual way. Okay, ignore the fact that some of these texts are in another language. The idea is that if on the input signal we have a positive voltage. Okay, we have this blue line, which is the ground. If on the input we have a positive voltage, so we have a signal above that ground, which is with the green in my case, the two output voltages, U1 and U2, are somewhat like this. We have a positive voltage on U1 and a very close to 0 volts but still positive voltage on U2. On the other hand, when the input signal flips polarity and we have this one with red, then the whole thing also flips with U1 and U2. We have voltage U1 close to 0 and voltage U2 at a certain value, so that their difference is equal to the input signal. Okay, and the ADC will constantly calculate U1 minus U2. Okay, you might be familiar with V. You guys typically call voltages V from voltage. We don't in our culture, so this is why you see U instead of V. Okay, V is for volts, U is for voltages, at least in my cultures and in a few around me as well. So basically on the digital side, when the ADC calculates U1 minus U2, if we are in the first version, in the first case with the green, the result will be positive, okay, and then in the second case with red, obviously the result will be negative because U1 will be smaller than U2. In spite of the fact that in both cases both U1 and U2 will be positive relative to the ground. Okay, and this is how the whole thing works and what needs to be done. Now let me show you some actual results on the oscilloscope. Remember, we have yellow and blue as the two outputs of the circuit. We have 2 volts per division in this case for both of them, and the 0 line is here. Okay, you take a look at this icon on the left which says 2, and with magenta we have the mathematical channel which has the 0 line here, the ground line here, and it has 5 volts per division in this particular case. So when I applied plus 9 volts to my circuit, well, plus and minus are arbitrarily chosen here because we really don't have a plus and a minus, you know. But anyway, we have the yellow at some 9 point something volts. The battery was a brand new battery which actually gave some 9.3 volts or something like that. So we have the yellow output at some 9 point something volts, the blue output at 0 or very, very close to 0, and therefore the mathematical difference is plus 9 point something volts. Okay. When I flipped polarity and I applied the same battery but in reverse, I have the exact different thing. I have the yellow voltage very close to the ground, the blue voltage at some 9 point something volts, and therefore relative to the mathematical 0 we have minus 9 point something volts. Okay. And so this is how everything works. And also I've done some extra tests with triangle wave signal on the input, ranging from 1 volts upwards, peak voltage, and we see that the ADC, the whole circuit, sorry, not the ADC, but the whole circuit works as expected. Okay, we have the yellow and blue waveforms, the 2 output channels of my circuit that are pretty much in opposition of phase, and they are a bit distorted, it is true, but overall if we calculate the difference we see the magenta waveform which is an actual triangle wave. Okay, it's not a perfect triangle wave because my signal generator is not perfect. It has various imperfections, but we'll get over that detail. Okay, and we have here 2 volts per division for all channels, and we see that we have about 4 point something volts peak, going both positive and negative. Okay, at 60 hertz, 61 hertz, I've also made some tests with these signals going fully positive, like in this case. Okay, you see the output, which is also the input with magenta, it does not go below 0, and we see how the 2 outputs on my circuit look like. Also, when the signal is only negative, so it never goes above 0, we see the exact opposite. The yellow is very close to 0 volts. The blue is a lot more positive, and the difference is still a triangle waveform. By the way, I use triangle waveforms because they are very good for checking linearity of pretty much any circuit. Okay, if you input a triangle waveform in a circuit that is supposed to be linear and you see something else on the output, then that circuit is not linear. Okay, but if you input a sine wave or a square wave, you have no way of figuring out what non-linearities you have in your circuit. So a triangle wave is perfect for checking linearities, and this is exactly what we want to check in this circuit. Okay. And also some more examples. I have also changed the frequencies. So we see this at 61 hertz. We see this at 21 kilohertz. And for me, for this particular circuit with 100 nanofarads capacitors on the input, 21 kilohertz was the maximum frequency that I could get without any form of attenuation of the signal. Above that, I get attenuation. So we have here the magenta signal, the output signal, has 500 millivolts per division, and the frequency is 208 kilohertz. And we see that, well, compared to 5 volts per division, where we have basically 10 volts peak to peak at 21 kilohertz, at 200 kilohertz we only have 1 volt peak to peak, or even less than 1 volt. Okay, because the frequency is too high and those capacitors act like a filter. But of course, if you need higher frequencies, you can just change those capacitors for different values. Okay. Still, the circuit still functions and does what it needs to do. Okay, so and this is what I wanted to see in these tests. Here is 1 kilohertz frequency, and that's pretty much it. Okay, I can show you a few more examples. This is at very low frequencies, at 16 hertz, with Schottky diodes. The input waveforms seem to be a bit weird. They are no longer triangle wave. But it's not a problem because overall the whole circuit still does its job properly, and we see with the magenta that the output signal is still triangular shape. Okay, so which is what's the input signal. So even if at lower frequencies the two voltages are a bit weird, and they seem to be deformed, overall it's still okay because their difference is still what it's supposed to be. Okay, now the same circuit with the Schottky diodes removed looks a bit like this at 35 Hertz. We see that we are starting to have some problems, some non-linearities. The output signal doesn't, we have 500 millivolts per division, so it goes from plus to minus 1 volts. We don't have phase reversals in this particular moment, but phase reversals can happen. But we clearly see non-linearities, you know, like here and here. So yeah, that's not that's not something that we want. So yeah, what can I say? That's pretty much it. It's not a big deal with this circuit, but it is absolutely necessary, and I hope now you understand why. Also, this circuit is necessary even if we have only positive voltages that we want to send to the ADC, but those voltages are not both referred to the ground, but they are two voltages that exist in two completely different places in the circuit. In that particular case, we do need to measure them through such a circuit, because otherwise we will have a short circuit if we try to forcibly create a ground somewhere, you know. So I hope you learned something new. I hope this was useful to you. Don't forget to like and hit the subscribe button if you enjoy this and plan to come here more often. If you're interested in electronics, I am making videos on a constant basis. Also, if you enjoy these lessons, these practical experiments that I'm making and I'm teaching you, please consider supporting me on Patreon. You have a link in the description. The faster, the more the more I can have money to buy components and devices, the faster I can learn, and also the faster I come here to you and show you what I've learned, so that you don't have to waste the time and energy that I'm wasting on learning these things. So thanks a lot for watching, and I will see you in the next video. Bye bye.